numbers to class 70 because usually are coming. So let a considerable crowd comes inside, then we will start them.
Sounds good.
What about you, Naina? Have you completed your coursework?
I completed a set of coursework, ma'am. It's unlike in India where we finish all our coursework in the initial year itself. Here you can gradually take the courses along with your PhD. So I completed around 7 courses. I have a couple more courses left, and you can also transfer credit from my masters. So I'm like halfway through my coursework, ma'am.
Very good. What about your research area?
That is also going on. You've started with some material testing in the lab and things like that. So today also after the meet today we have a test in the lab. So that's also going interestingly, ma'am. Thank you. How is the department, ma'am? How is the students?
Here the situation is very critical. That's why we are close to the past 1 year. Students are
online classes.
Only such programs only we have to see them. Classes online classes. Among the students come from this now it is a full lockdown. No meeting physically. Now the things are better. Your mom was telling for you.
As in the COVID situation, ma'am?
Yeah, COVID situation.
Yes. I mean, the entire US, it's pretty under control. I mean, everybody's getting vaccinated and things like that, so it's pretty okay, ma'am.
Your place is safest, she was telling.
God bless.
It would be at least somebody is comfortable means we feel happy. What about your friends? Are they joining you?
I am not sure, ma'am. I think Gopi might join in, but I'm not sure, ma'am.
Gopi, yeah. He's now working, no?
Exactly. So if he's done with his day's work, then he might be able to, but else he might not.
Surrender sir, have you joined? Surrender is not here.
No, ma'am, he didn't join.
If he has joined, we can ask him to inform alumni students also to join.
I'll call him and tell him.
We will wait up to 70, madam, then we will start.
Sure, ma'am, sure.
I recognize the red cup of coffee in your hand, Ramla, and I'm jealous of you.
This is my morning petrol. I cannot function without it. So. Some bad habits that we pick up during PhD. One of them is addiction to coffee.
Definitely.
What about you? Have you finished? Where to start? Coffee.
Coffee addiction, for me, it began in master's itself. I was a step early in that.
Okay. What time it is there?
For me, it's 7:30. For Ramla, it should be 8:30.
Yeah.
But it is very early for a webinar to start for you.
little bit early. One of the reasons why I was able to get up early, ma'am. So it's good that it happened this early. At least the day will begin early.
But here it is 6 in the evening 6.
6, yes.
Ajit Gaurav have raised the hand. Ajit Gaurav, you have raised the hand. Any doubts you want to ask? Maybe unknowingly he may have touched it. Yeah, for this series, 4 of our alumni have taken part, Naina. That is a good news.
Oh, that's so nice, ma'am. It feels so good to come back and talk to these students about the things that we learned after graduating and things like that.
They are all working abroad, so they share their experience. It was very nice to hear from them what and all the softwares required they updated, how that AR, VR technologies are used in construction management.
Mm, true.
That they were
We,
all.
I remember we had a guest lecture in the end of our bridge design course in which they talked about AR VR, where they were like, before you construct itself, you can see where you would imagine things being placed, and that'll give an idea to the students. I mean, that'll give the idea to the designer on where to place, what to place, how to place, and it's definitely important. So it's definitely an emerging technology.
And now for our final year students, the present third year to final year students, we have introduced
Mm,
BIM as a training course.
nice, nice, nice.
BIM as a training course, they will be for a semester. They will be having the training and internship
Nice, ma'am.
in the real-time projects.
Nice.
Only
BIM
this
was also one of the concepts that we had guest lectures on. Definitely, those are good topics to introduce to them, ma'am.
technologies the students should know.
I mean, at the first go, they may not get the overall picture, but with continuous contact to the topic, they'll develop the interest in it and they'll go in deep by themselves itself.
Yeah,
So that's definitely important.
that is how we can assist for helping them to become an entrepreneur.
Mm.
They can take a real-time project, and that is what the idea behind it. Because the
Okay.
company, those who are having some projects in BIM only coming and giving the training. So
Nice,
if
ma'am. Nice.
they are interested, they can start up and have some small contracts, a bit of their work they can complete in BIM,
Nice.
and they can be on their own.
It's like, so they essentially wouldn't be freshers when they graduate. They do have an experience. They're like, I do have a 6 month experience of working in BIM, so that's definitely great for them.
Yeah, all the final year students will have minimum of 6 months industrial experience when they leave this college. That is the idea behind it.
Very nice, ma'am.
Uh, we will start, I think. Chandrakantama, madam, shall we start? Madam, I think
Yes, ma'am. Yes, ma'am. 76 have joined. They are joining, ma'am. We'll start. Yeah,
good
ma'am.
evening to all the participants. We have come to the last day of our international webinar series. I'm glad to welcome Dr. Ramla Qureshi from Department of Civil and Environmental Engineering, University of Buffalo, from State University of New York. Welcome, Ramla. This is another important and happiest occasion for us to hear from you. Thank you for accepting our invitation. And the topic is also very interesting for some of the participants. The participants include some teaching from the fraternity. Some of the research scholars also have joined. Those who are post-graduating, they have also, some of the participants are postgraduates. So this area where the testing of structural elements under the natural hazards. This will be an interesting topic for them, how to test it in dynamic properties, how to catch up for the structural elements. This will be yet another interesting topic. Everybody wants to know. So thank you for accepting our invitation and welcome on behalf of Civil Department of SRM EASWARI Engineering College. I welcome our alumni student Naina Kumar also and all the participants for this last day of the webinar. Chandrakantama madam,
Ma'am.
please
Yes, ma'am.
take
Yes.
the
Over
session
to
and
Sneha.
introduce the guest.
A wonderful evening to all who have gathered here for the international webinar series on innovative technology on civil engineering on behalf of Department of Civil Engineering, EASWARI Engineering College. Today's topic for the session is intersections of structural resilience and data science in natural hazards context, followed by a Q&A session. Now I take immense pleasure in welcoming our guest speaker, Dr. Ramla K. Qureshi, Engineer in Training, Department of Civil Engineering and Environmental Engineering, University of Buffalo, the State University of New York. She has completed bachelor's from National University of Science and Technology, MSc Civil Engineering and PhD from University of Buffalo, the State University of New York with AAUW Doctoral Fellowship and Fulbright Scholarship Award. She has research experience as structural and test engineer from Structural Engineering and Earthwork Simulation Laboratory, as graduate research assistant from University at Buffalo. She also has industry experience as structural engineering intern from Ketana Consulting Engineers Portland, as structural engineer design from Descon Integrated Projects Private Limited, Karachi, Pakistan. She has published many research papers in reputed journals and conferences. She has received NSF Award for 2021 National Hazard Engineering Research Infrastructure Summer Institute, Best Student Paper Award and Best Student Presentation Award at 11th International Conference on Structures in Fire, Australia. Chairs Recognition Award from University of Buffalo. Professional Development Award. UB representative for 6th Annual AAAS Catalyzing Advocacy for Science and Engineering Workshop. Leaders in Excellence Award. Certificate of Excellence in Research, Scholarship and Creativity. Best Poster Award. First prize at UB Sustainability World's Challenge for Project Elevator and much more. She is the founder and CEO of Women Engineers Pakistan, member at Women in STEM International Working Groups on Practice, Institute of Learning Innovation USA in 2021, World Bank Strategic Partner for South Asia Women in Power and Energy Network in 2018. She provides advocacy, training opportunities, and academia to industry networking. She has trained diverse student teams in 15 universities, conducted outreach to 4,000 plus schoolgirls, and curated high-value professional network of 1,000 plus women in science and engineering. We welcome you, ma'am. Ma'am, now you can proceed with the session.
Thank you so much, Sneha. I had major imposter syndrome when you were reading out. I was like, who is she talking about? Thank you so much for having me here. It's absolutely an honor. I can imagine it's 6 p.m. in India, so I am honestly very, very grateful for the amount of people who showed up. May I share my screen?
Yeah. There is a present now icon, no? You can touch it.
Okay.
That will share the screen.
Can everyone see my screen?
No. Yeah, now it is starting.
Okay.
You can share the presentation also. Yes.
Yeah.
Yeah. And can you see it now?
Yes.
Yeah.
Awesome.
Yeah.
Awesome. All right. So like Sneha said, my name is Ramla Qureshi. I recently completed my PhD education from the State University of New York in December 2020. Not a really great time to graduate in the middle of a pandemic. But if you notice the topics that we're going to talk about right now, I think whatever I learned about structural resilience, I was able to sort of practice in my personal life as well. Before we kick off the presentation, I would like to talk a little bit about my current expertise. I am by training a structural and earthquake engineer. Nayana and I, we did the same master's program. I'm not sure, Nana, if you were in bridge or structures, but it's a pretty holistic program where the major dynamic hazard that we are taught for is earthquakes. So when I sort of proceeded into my PhD degree, I realized, okay, now I have to do a whole other specialization all over again. that included a lot of work on structural fire engineering, a lot of work on, protective design engineering, prevention against impact loads, terrorist attacks, prevention against different sorts of hazards. I didn't work a lot in floods, but we realized that, okay, natural hazards include a lot of different impending disasters that we as engineers need to be prepared for. And simultaneously, I had the privilege to sort of grow my research and talk about, risk assessments, as well as some intensive reliability analysis, uncertainty modeling. And a lot of that is what I will be presenting today, because a lot of that has the need for data and open access data and good quality data as well. Of course, any PhD requires a lot of coding and programming, but I was also able to develop a software tool for industry applications, particularly surrounding risk assessment models. And if I get a chance, I'd like to talk a little bit about that as well. And of course, experimental mechanics, because I did have to do a lot of hybrid simulation, but I won't go into that because that's a topic for another day or week, perhaps. So let me start with some extreme hazards, right? We know that concept of resilience, if I dig a little bit deeper into that, it's previously been very comprehensively defined as, number one, the resistance to an unusual external shock. And we call this resistance as robustness. And number two, the ability to recover quickly from this shock. So this we often term as rapidity. So if I base my upcoming slides on this topic, that's it. That means both robustness and the ability to recover quickly. We know that previous studies have explained that resilience comprises of quantitative assessment as well as qualitative assessment methods that can evaluate this robustness, and strategies that can help improve this resilience. So, for example, policy measures, and for example, preparation and prevention, right? So we know that among these disaster resilience studies previously, globally, by the way, these disasters have included earthquakes, hurricanes. I mean, as we speak, we are talking about a intensive cyclone in the southern parts of India as well as Pakistan, floods based on heavy rains, based on glacial melting, based on many different topics, based on politics as well, and fires. So fires we see a lot in North America. 2020 started with Australian bushfires. Not that many of us remember what a disaster that was, because that was just the start of 2020. But that's a lot. There's a lot to be said about wildfires and urban interactions with dense ecological systems. Now, I'm showing these photos here. The first photo is an earthquake from, it's a 8.2 magnitude earthquake in Matias Romero in Mexico. This was back in 2017, if you remember. This is a very, for folks who are interested in earthquake engineering, this was very monumental because it did lead to quite a lot of damage, right? And then on the extreme right side of this slide, I'm showing a photo from the Rim Fire. This burned over 1,000 square kilometers of forest near the Yosemite National Park in the USA in 2013. We've seen recurring wildfires ever since, because there's multiple, of course, reasons for that. One of them is human intervention, human activity. We have been artificially suppressing the natural process of wildfires. So now whenever they happen, it's way worse than what we expect. And the middle photo here is a recent flood in 2020 in the middle of the pandemic in Karachi, Pakistan, after intensive rainfall. So a lot of these extreme hazards, while they may seem like isolated events, I want you to think of them as cascading disasters, because uh, while extreme hazards like earthquakes, etc., have a period of return period, um, they are never these disasters don't ever come alone. One thing, while we talk about extreme hazards as engineers and as civil and structural engineers, one thing that is very important to keep in mind is that earthquakes don't kill people, floods don't kill people, wildfires don't kill people, damaged buildings kill people, bad infrastructure, bad um, uh, sewage, bad what's the word? Some hydrological word that is just escaping my brain right now. Um, Bad management, right? Bad engineering kills people. So before I go deeper into the very mathematical aspects of this, I always like to start and indulge my audience with this thing that has been bothering me for some time, that in pop culture and pop media, we never really see TV series and TV shows that, where the civil engineer is the hero, right? We see tons of series and interesting TV shows and drama serials regarding Silicon Valley, regarding hospitals and surgery and all of that, but never a civil engineer. And I was discussing with my husband, and we realized that there's a solid reason for that. It's because our entire job as civil engineers is to make life boring for people. Our entire job is to ensure that nothing monumental happens in the everyday life of people who are not civil engineers, right? So it is our entire job to stay behind the curtain, right? We are the off the curtain heroes. That is perhaps why a lot of the work that we do is held in academia and research, but not so much in pop culture. And that is also why, and hold on to this, because some of my last slides are important in this topic, because I think now is the time we bridge that gap and actually talk to people who are, well, I don't like calling people laymen because they may be very smart, but they may not necessarily align with civil engineering, or they may not necessarily have intensive information about civil engineering. So now I believe is the time to talk about all the work that we do, talk about the disaster resilience. One of my professors from Karachi has written books in Urdu that target contractors in Karachi, in Pakistan, and talk about earthquakes, right? We call it zilzali. And I suggest we as engineers and engineering students now start writing in our native languages and start talking to our parents and our families and our audiences in general about why extreme hazards now require everybody's input. Now, we talked about some natural hazards. We did not talk about man-made hazards. Man-made hazards are also very, very important to know, because we saw this in Beirut, right? Everybody, well, it shook the entire world, because this happened because of human negligence. This was one of the biggest impact load that the world has seen since they dropped the nuclear bomb, right? Exactly. Chandu, I think, is writing in Lebanon. That's correct. This happened in Beirut, Lebanon. And as civil engineers, I know I shouldn't have been excited, but somehow there was this, perverse sort of excitement that, yes, now I can talk about this. Now I can talk about why it's important to protect buildings against disasters waiting to happen, man-made disasters waiting to happen, and also categorize this in the extreme hazards. India, Pakistan, and Latin American countries, I believe Bangladesh as well. So these countries are the top 10 countries that have the biggest probability in the next 10 years to be affected by climate-related extreme weather events. That means that natural hazards are right there, right there. We are now graduating into a world that directly needs our input. So it's now important to start thinking about all sorts of solutions. And when we talk about resilience and sustainability, we need to understand that man-made hazards are also part of all of that conversation. And of course, structural fires. Now, I tend to keep structural fires as a separate category of its own because it can be both natural, it can be man-made as well, like arson, uh, just human mistakes and human errors. This is the Grenfell Fire in London back in 2017. It made waves around the world. I should have probably put the Notre Dame fire here, but it's important to realize why I put structural fire, but the Grenfell Tower here, because first of all, this was a disaster waiting to happen. This was a facade fire that ended up taking about 72 lives, if I'm not wrong. And to this day, none of these people have been recompensated. Well, you can't recompensate life, but because people can't pinpoint whose mistake was it. And in my mind, it's a fire protection engineer's mistake, right? So now that we've covered a bit of the basics of where I'm coming from, I hope you can hang on to these photos and these topics as we move into, some of the more denser details about this topic. Now, let me start with, because we're talking a lot about data science, let me talk a little bit about what is ground zero, what is square one right now. We know that over the past 2 decades, we have had over 1 million deaths just because of fire incidents. Now, I'm going to talk a little bit about fire incidents based on the fact that that is my choice of natural hazards right now, and also because we have a lot of data when it comes to fire and earthquake. So I chose fire because we in South Asia don't really talk that much about fire, whereas we have some of the highest numbers in fatalities. In 2018, on average, just in 2018, in the USA, a fire department responded to a residential fire every 24 seconds, right? A structural fire occurred every 63 seconds. A home fire occurred every 87 seconds. And an outside property fire, like in a garage or in an empty plot, that occurred every 52 seconds. In highway type, vehicular accidents and these fires, those were also fairly common, and they happened every 2 minutes, 54 seconds, so every 3 minutes. Now, if you somebody who is a math whiz can basically extrapolate and count how many these happen to be in a year, but this is just an average figure, and that to me is very scary. As somebody who trained to be a resilience engineer and a risk assessment engineer, these numbers are very scary. So in the US, in the developed world, the USA tops the charts when it comes to fire-related deaths and fire events. And it obviously costs a lot of money. It costs a lot of money to rehabilitate, to retrofit. Many, many times after fire, structures are deemed to have insufficient strength to be livable or to be functional or to be safe, right? Post earthquake, sometimes that happens, that engineers can do, a forensic analysis and say all is well. Many, many times after fire, buildings have to be demolished. So that is one thing we need to think about as well. But let's hit the nail a little bit closer to home. In the developing world, for us in India and Pakistan lead in fire casualties. Every year, we have between 10 to 25,000 deaths, just the two countries. And I imagine that, okay, we are also very populous countries, but that means we have all the more reason to protect our people from these hazards. Based on some statistics provided by the Rescue 1122 website in Punjab, in Pakistan, there were 135,000 recorded fire emergencies just over the last decade and a half. And out of this 135,000 events, 32,000 happened in the city of Lahore. And coming from a government website, I can assure you the number is far more, right? So talking about all of these things leads me to a natural progression of talking about the resilience framework. This was work done by my master's thesis advisor, Professor Michel Bruno, back in 2003. He's done a lot of work in earthquake engineering, and if I may go into a little bit of detail about this figure, it shows that with the passage of time, a structural system, because we are civil structural engineers, or let's say a network, because we are also infrastructure engineers, bridge, roadways, highways, or a community, because like I said, our job was to make life boring for other people. So all of these people, all of these systems may maintain a certain level of functionality, right? Or they may enhance this level by improving the status of different components of different systems. They can go into prevention measures, or they can experience a decline in this functionality due to the process of aging, right? Buildings and structures age as well. Traffic ages as well. As traffic engineers, we know that we estimate for traffic to increase exponentially as 50, 100 years move. But what happens when a sudden shock is experienced by this community? Sudden shocks such as earthquakes, hurricanes, or man-made disasters. What happens is this sudden shock causes a decline, a sudden drop in the operability of the systems. Now, resilience then is related to the residual level of functionality after this event has happened, as well as the functionality up until restoration time to normal operation, right? So what is the measure of resilience of any community is how it functions when disaster hits. So what my professor mentioned in this technical report is that during restoration and repairs, we have an opportunity that we increase the functionality level to higher than that was available, prior to the sudden disturbance, and that may help exponentially improve the functionality levels of communities. Since we've been talking about communities, let's talk a little bit about urban resilience. Now, urban resilience is a very similar concept, but urban resilience sort of loops in politicians, policymakers, finance people, organizations like the World Bank and the UN and the governments. Urban resilience by definition, so I'm going to cheat the definition from Rockefeller Foundation, and they mentioned that urban resilience is the capacity of individuals, communities, institutions, businesses, and systems within a city to survive, adapt, and grow, no matter what kind of chronic stresses or acute shocks they experience. So the idea is that even in the midst of a pandemic, for example, or a flood or a fire or an earthquake, a city should have that much redundancies and resilience measures that it should be able to not only survive, but adapt as well as grow, no matter what kind of shock it faces. However, cities are very complicated systems. In fact, they are system of systems, right? They contain a multitude of physical elements, right? We talked about buildings, we talked about transportation. There is, of course, also, pipe network systems, right? Electricity systems, telephone and internet network systems, as well as non-physical elements such as, social, economic, and ecosystems as well. And there's how can I say this? There's a very complex relationship amongst different systems, right? So we need to understand as engineers that we cannot remain in silos, right? we cannot keep working in our own echo chambers. That is where the multidisciplinary perspective of resilience, and specifically urban resilience, comes into play. Now, how can data help build urban resilience? And that is the question that we will focus on as we move forward. We understand that, urban systems interact with many different ecological parameters. Many of our cities are built on the fringes of forests, specifically in South Asia. Cities sort of evolved along river lines, right? So we suffer from all kinds of natural disasters as well. In this figure that I've taken from a 2012 book on urban resilience, it's called Urban Resilience Towards an Integrated Approach. They presented a really nice Venn diagram about what exactly is urban resilience. And they talk about the integration of, not only infrastructure resilience, or just engineering resilience, but also the resilience of ecological systems, implying that if I have built a city on a river bed or along a river line, did I ensure that I did not harm any environment there, right? And we also need to talk about social resilience. So, for example, the interaction between SES, which is social economic, implying that if somebody's livelihood is dependent on timber and lumber, right? That means they will have to go chop out forests. But are we growing more forests to replace that? So what is the social ecological resilience? As well as STS resilience. Now that is social technical resilience, which we saw a little bit of a glimpse of it in the middle of this pandemic. By the way, the pandemic is also a natural disaster, right? Which, if you think about it, if we had prepared for pandemics in a civil engineering point of view, we would have created redundancies, redundant places which were functional, which can house patients in a hygienic way. We would have created homes that gave people the choice to isolate. Many times we saw people saying, well, social distance, blah, blah, blah. Socially distancing was a huge privilege in our countries, right? And we as engineers now need to think of this, that how can I as an engineer help in creating the socio-technical systems, and how can I increase their resilience? Now, I won't go into other parts like individual, psychological resilience or market and economic resilience, because other people would do, more of a better job than I can in this. But let me assure you that what we do as civil engineers helps in each and every single aspect of this, including psychological resilience. Now, let me come back to the question of how can data help us in all of this context. And because I focused more on fires, let me focus a little bit on this particular extreme hazard. Where we come from in USA, we don't see that many wildfires. But on the West Coast in California, this is a yearly hazard that people tend to prepare for, and yet we see disasters every year. That implies that this disaster is increasing, and that implies that we have data missing, because we cannot properly calibrate what to prepare for. So we know that while California's major wildfires have been contained, and some of them have been, well, major disasters, but the heroes and firefighters have really helped contain it, the threat of bigger and more destructive blazes is always there. Because, of course, number one, climate change. Climate change exacerbates the chance of much larger magnitudes of wildfires, specifically because there's drying out vegetation, and it serves as fuel, for firestorms. And what is happening is because California and cities in California are insanely expensive to live in, um, human population, I would say, is now breaching into wildlands, right? We have started building into wildlands. Now that is where the interaction with an ecological system comes in, and this increases the risk of destructive fire increases, specifically because human beings tend to light fires. We tend to be careless. We tend to somehow, as teenagers, also be reckless. And a lot of these wildfires, I'm not sure how much of information is presented to the rest of the world, but we know that a lot of these wildfires started as a result of celebrative events like gender reveal events or weddings and things of that sort. So a lot of these were actually human activity, right? Now, we have data from the past 9 years from a lot of California counties. However, there are a few counties that we have absolutely no idea about. So what we have done is that as engineers, we are really good with math. So we have extrapolated some of this data, and we have also manually extracted this data, right? How can we do that? Some of it is, well, you go deploy sensors and sensor networks. These are low-cost gadgets, and you sort of backtrack based on wind data. Or you go talk to people and ask them their lived experiences, and data. So what we did in our research group was, first we needed to understand what are the urban features of California, right? We needed to understand topography and ground elevation. We needed to understand what is the average wind speed and wind gusts. We needed to understand how do people build. Do they use concrete blocks? Do they use brick masonry? Clay masonry? Do they use wood and timber, or what sort of construction is happening? We also needed to know what kind of vegetation is surrounding these communities, and whether or not there are active fire suppression networks and water networks available. Now, I know I've written this in words, but all of this is intensive data. All of this is intensive data collection in databases. So my colleague Nima Masood Waziri made, what he did is that he overlaid the topographical data of California that he got via satellite data with the average wind gusts, right, from some climate reanalysis models. And he was able to attain a measure of what can be a range of expected fire data in those missing counties of California. Because we understand that a lot of these things were, excuse me. For example, wind is one of the major reasons for fire branding, right? If there is fire happening in a forest nearby, it's the wind that causes it to jump and reach urban settlements. So if we have this data available, we as engineers can combine a lot of available data and extract information from it, right? Data, I'm sure most of you have seen that meme that data can be just a jumble of things and certainly would make no sense. That's where data science comes in, because you have to extract the patterns and you have to be so vigilant about taking in data that actually matters, right? And understanding what data matters and what doesn't. So let me talk a little bit about one of the case studies that was done on a similar concept in California, right? This is the Tubbs Fire. It was one of the most destructive wildfires in California. It destroyed over 5,200 homes and killed at least 22 people in and around the city. In this region, winds exceeded sometimes 50 miles per hour. So it's a highly windy area. And what was happening was that communities were gradually being exposed to faster spreading wildfires, right? And for this case study to be conducted, we had to understand the integrative fire spread models for urban settlements. So what we'll do is we'll pick up, many different settlements here. Let me see if my pointer works. So settlements here, if you see there's one here, multiple settlements here, one is here. So what we're going to do is we're going to go talk a little bit about this Fountain Grove settlement, right? And see how this Fountain Grove community suffered from this fire. So if I have to now predict fire spread from communities, now I also need data input, correct? So I need to understand what is the footprint of buildings, meaning how far apart are they? Distance is very important in this. We need to know how much of combustible material was available there. That includes timber buildings, that includes vegetation and landscaping around, that includes people storing combustible material like logs and timbers in their homes. We also obviously need to, like I said, need to know what's the type of construction, whether it was single story or double story. That's important because if there is fire branding happening from tall trees, a double story building is more susceptible to getting ignition, being ignited, as compared to a single story building, right? And also we needed to understand physics-based data on radiation, on fire branding, and also direct flame contact. And this in itself is a whole thesis because there's a lot of data that needs to be collected in order to create predictive models. Now, we know that fire lines, as engineers and as people who work in applied physics, we know that this consists of, three primary processes: thermal radiation, direct flame contact, as well as branding. And while we in our research group are talking about this, we understand that a comprehensive model that predicts how the fire would travel would integrate all of these three mechanisms. But as of now, well, before the animation that I'm about to show you existed, such a model for understanding wildland urban fires did not exist at all. So we did a lot of data collection and created the model that I'm about to show you now. So as you see, from left to right, we're showing the movement of this fire. And red is when the buildings, the houses are currently under fire. And as the wind moves, now all of these buildings have already been ignited. If you see, it's moving, but not all the buildings were readily getting, some of them remained black, and they only got blue or red after a while because the building next to them was on fire. So a lot of this also happened because of radiation. We talked about community urban interactions with wildfires. Now let's talk about city areas where perhaps fire is a structural fire and has nothing to do with wildfires, right? It is perhaps a residential fire, or it is perhaps an ignition that happened post-earthquake, right? What is happening in this particular diagram is us as engineers trying to understand the event tree analysis of what happens in case there's an earthquake or a fire. And as you can see, that every single transportation and every single network, so for example, transportation, water, electric, roadway accessibility, all of these things combined were necessary for us to understand how can firefighters come help the suppression. Now, if there is an earthquake, or if it's not even an earthquake, let's say there is a vehicle impact with a building, right? There's probably some sort of structural damage happening there as well. And that implies that my structure already is not strong enough to sustain a fire damage. So all of this is important when we think of urban resilience, because we have to understand all these different scenarios that things can go wrong in. How can we build models that help something of this sort? That is where in knowledge of GIS layers really helps, right? That is where we need to have sort of overlays of community data, right? Census tract data implies how dense a community is, what is the population, is this a senior living, is this a school, sort of understand the age group that you're targeting. Are these people agile enough? Are these people adults to understand that there is a fire and they need to evacuate? All of these things. Plus, then you have to have the hazard map data, which I showed you that for the California fires that we were talking about. You also need to understand transportation networks. Why? Because if there is a fire, you need to be, as engineers, if you're creating a resilience model, you need to be able to know, for example, how long would it take for an ambulance to reach this particular place? How long would it take a fire brigade to reach this particular place? That implies you need to know if it's rush hour, you need to know what's the live traffic data. You need to know if the roadway is accessible, right? You need to have a lot of data that comes into this model. For fire, as well as for earthquakes, by the way, you need to know the water network. For example, sometimes what happens is that water pressures are not viable for fire mitigation. So you need to know where's your next best approach as well as electric networks, because, well, a lot of ignitions happen because of electric sparks, especially post-fire, post-earthquake cascading fires are almost always because of electric sparks. So we need to know how and where the electric network integrates with the social and the community network. So what we did is that we took all of this data from a city in USA. I am not at liberty to say what city this is, but let me assure you this is an actual city. We're calling it a model city because we do not have liberty to say what city this is. And we created a whole resilience model for this city. Now, if I go a little bit into depth of this, let's say there is a built environment map for this city. And these red dots here are the ignitions that have started in certain buildings, because let's say there was an earthquake and electric spark happened and these buildings are now on fire, right? The next thing that we wanted to know was the water network. So we wanted to know if all the nodes in the water network had sufficient pressure or not, because this is the data that I want to give my fire brigades and my fire mitigation people who are helping out at the area of the disaster. So that is also my responsibility to understand that. And if you can see, there's two major water pumps here and one auxiliary water pump. So two major are at the top and bottom shown there, and the auxiliary one is at the right. And then lastly, in this model, we wanted to understand the transportation network as well, because we want to know if the fire engine has any alternate routes which are faster, or how far the fire station is from the area of the fire hazard, right? And by the way, more often than not, roadways are not accessible. Let's say in the case of a cascading fire, there's been an earthquake, right? So the USA infrastructure is not great. USA recently said, okay, we need I don't know, $6 billion to upgrade our infrastructure. So a lot of these include bridges that are close to failure. So if we call it a design earthquake because that's an extreme earthquake. If that happens, we expect that there will be debris, there will be lack of access for all these different life-saving, fire brigades, ambulances, doctors, everybody. So this is important for us to realize that bridge taxonomy as well as transportation networks needs to be really, really agile. So for the transportation network analysis, we took into account something called fragility curves. Fragility curves are, for those who are interested in data science would know this better, that fragility curves are giving you probabilities of reaching a certain damage or reaching failure. But this was an intensive inventory created by my colleague Amir Saresh Tadari, and he took into account, all these older models and parameters that we require for earthquake fragility curves. And they were established to provide a sort of prediction of potential damage that can happen to bridges in the US during an earthquake. And as you can see, it looks like, a very nice, clean GUI tool, but it took him a whole year to come up with this, and it has a lot of data behind it as well. And if you can see, it also takes into account what is the type of superstructure, what was the intensity of the earthquake. If it was a bridge, what is the number of spans, what is the number of columns, what's the type of joint. Every single thing was required for him to create something of this sort. And now industry folk can just input whatever they want and pick out a certain probability of failure, and then back calculate or reverse engineer their performance objectives for a certain disaster measure, as well as a certain performance level, that whether they want it to be safe or they want it to be functional. Now, moving to, I know I talked a little bit about communities, then I talked a little bit about cities. Let's move from communities and cities to individual buildings, right? And in that, we have a very desperate need to come up with risk-informed and experimentally validated procedures that can advance structural fire engineering. This requires, the development of standard methodologies for risk assessments and reliability analysis of structures at elevated temperatures, but it's a full Pandora box of a multitude of uncertainties and inherent randomness in structural fire safety. I mean, let's say there's a fire in a particular room in a compartment. As civil engineers, do we know exactly what this room was being put to use for? For example, I know for a fact that in our countries in South Asia, residential areas are used as storage places and storage places are used as residential areas, and we abuse structural systems to no end, right? So there is uncertainties, and it's a data science engineer's nightmare that there is such a range of uncertainty and randomness in how local trends exist in Pakistan, in India, in Bangladesh, and these countries. But we also don't know what is the dynamics of the fire, because we tend to build, how do I say this, like containers, right? We don't tend to build spacious houses with proper ventilation or proper access. And we also do not, as engineers, we also are not really ever, at least in our undergraduate education, we aren't really ever told fire hazards in too much detail. It has, again, a lot to do with how, as a society, we haven't really picked on different hazards yet. And we really need to now communicate, as engineers, we need to communicate all of these different things that I talked about today to our communities as well. If I pick just, just the fuel uncertainty. Uh, um, there's a lot of work to be done in this. Even in the USA, by the way, the last time a comprehensive combustion fuel survey was done was back in the 60s. So just now, the NFPA issued different grants. One of those was to Nayana and my supervisor, Professor Nigar Ilhami Khurasani, and it was for research titled Digitized Fuel Load Survey Method Using Machine Vision. Sounds really fancy, but it's not. And let me tell you why it's not, because everybody has a phone now, right? So all of us can now assist in creating this sort of surveys. How this happens is that we predict fuel load densities, which in a nutshell is basically how much rate of heat release can you expect from a certain material over a certain time, right? So we wanted reliable fuel load data to quantify what sort of fires do we expect for buildings. And obviously, like I said, nothing recent was available. And why was that important? Because buildings and structures and usabilities have changed since the 1960s. We now rely more on digital. We have lots more wires. We have batteries. We have less paper, perhaps, but we still have uh, different kinds of fuel available now. And we have very differently for a fire. So what we did in this project was to develop a new methodology that facilitates the collection, the storage, as well as the analysis of available fuel load data for different building occupancies. What happened was that we came up with a 4-step method. What that 4-step method is that, number one, we do digital inventory. What happens is that you go into a room, you start clicking photos of everything. If you have an iPhone, you can actually, or you could use a variety of different apps in Android as well. You can come up with dimensions by just clicking photos, right? Yay, technology. So if you have dimensions, for example, you could just come up with area, multiply that area with whatever fuel load you have from an industry test or a lab test for wood and timber, for example. But let's say, what happens if you have a chair of this kind? This is a standard office chair. We see it in every other office. We were able to get the dimensions. What happens then? So let's say we did the digital inventory, right? And we took photos and we did the whole data organization. Next, we had to do item matching. I know it says machine vision, and it is machine vision, but I'm sure all of you are aware of the search by image function in Google. You search by image, you get thousands of chairs that are exactly like that. And then we found out that, okay, what is the exact mass of this from Amazon? And we were able to come up with a total of 10.4 kilograms using computer vision. And because of that, if I go back and I say, okay, I understand the caloric value of plastic or of metal, I can then calculate my fuel load for a particular office or a particular use case scenario. That tells me this entire research was actually, I consider it completely revolutionary, because that tells me that citizen engagement can assist so much more in a exhaustive, well, comprehensive model for fire fuel surveys. I know we talked a little bit about fuel load, we talked about fire dynamics. We now need to talk about construction materials. And I'm sure you all know every material, even though concrete, we use a standard weight, we use a standard empirical strength, we use a standard empirical modulus of elasticity. There is a lot of uncertainty in both steel and concrete, right? This was well, these are about 1,000 data points. These are about 500 data points that I found out manually going through many research papers explaining lab tests. And even at 20 degrees for steel, you can see that there is and by the way, this is normalized data points, meaning that each one of these data points was divided by yield strength at 20 degrees Celsius. You can still see that there was one particular test that said, oh, by the way, at 20 degrees, I am like 1.2 times, 20% more. So there's a lot of inherent uncertainties and randomness, even in material data. And I am not sure how it is in India, but a lot of times in my country, in Pakistan, we sort of copy paste things from British codes and ACI, and we don't take into account that a lot of local material behaves quite differently, specifically for concrete, because concrete is an amalgamation of different things, and a lot of local aggregates really matter for that. So perhaps somebody in India can replicate this study and see how it varies, see if the construction materials are different, and how different are they. Even though you can see a trend for steel, concrete was just haphazard. Concrete material, and this is, by the way, the strength retention as I increased temperature in Celsius. So we had to come up with a probabilistic approach to quantify this uncertainty and realize that we need newer material models for analyzing post-fire strengths. And if I am designing for tall buildings means high-rise buildings that are only limited by fire evacuation protocols, right? So we need to now understand what is the trend of strength that I have as my material is heating up. One problem that we realized in my research for construction materials was that a lot of these lab tests are done where it's just a beam or just a column and you've put it on fire, and you never really take into account that buildings have redundancies. Remember the moment redistribution things that we used to do? That's where it actually is applied here, is because, well, if one member is losing its capacity and its strength, other parts of my building are taking up more of that strength. So in just, element level tests, we potentially ignore a lot of strength that is available through redundancies. And that's why I mentioned that we don't really know what is global structural behavior when it comes to fire. And again, that's where a lot of data comes into play. Let me talk a little bit about how we came up with these stochastic models. I know I'm running a little bit short in time, but we created, so by the way, to all data science enthusiasts over there, let me assure you that all data models are just that. They are models. They can never be reality, right? Because reality will always be different. So you, as an engineer, can either kill yourself by trying to make it as accurate as possible to a realistic scenario, and then the next time it happens, it's again different. Or you can come up with something that is, the next best way and move on and provide a range, right? So we decided that let's test 13 different probabilistic density functions and see which model works the best. And we realized that if I was getting a time to failure for, let's say, a steel column for, 37 minutes, it's an unprotected, uninsulated steel column, just coming up with a wild number here. with one distribution function. The other distribution function basically just gave me, I don't know, 32.5 minutes. Like, it really didn't matter that much. So we came to the conclusion that while it's really, really important to integrate uncertainties and come up with stochastic models, the choice of that model really doesn't matter. And to sum up this entire conversation, I talked about how using data science, we can come up with, resilience measures, not only for our regions, but also for community levels, for building levels, understand different compartments and their inherent randomness is available, as well as the uncertainties that we have in material models. And this is the whole range of work that we are doing here at UB. But let me tell you, there's a lot of ground to cover. So if there are other enthusiasts in data science, please feel free to reach out. Please feel free to work on this, not just in fire, but with all the other natural and man-made hazards that we talked about at the start of this presentation, because we now need a lot of reliable and risk-averse engineering. We can't just blindly put empirical formulas anymore. We need to have a robust understanding of what it means to the building that we are creating. Ultimately, our job is to make life boring for other people. However, we can always seek their help, right? Like I said, that now that we know that we need data, we as engineers, especially we as civil engineers, need to go out into our communities and do a lot of outreach. We need to take into account citizen science. I know that there's this whole buzz of, Internet of Things and smart cities and all of that. Know that most of this is just jargon. A lot of work that we do is statistics and probability and intensive data collection, right? Smart cities, I tend to not talk a little bit about that because there's then the whole question on, privacy and all of that. But as far as we as civil engineers are concerned, we can actively take input from fellow citizens. For example, in the case of earthquakes and fires here, the United States Geological Services USGS takes, did you feel it, damage maps. So if somebody said, oh my God, there was an earthquake in California, in South California, and somebody in North California didn't even feel it. So while this is not, accurate scientific data, it helps to validate your data. It helps to extrapolate your data. Human experiences are very, very important in that regard because you want to know, is this even correct? Is this even true? Most of you would have seen the Facebook mark yourself as safe data collection as well. Many people do that. That is also citizen science, and that's very, very helpful for data science engineers. Simultaneously, we need teaching initiatives. We need each and every one of you, hopefully all the 92 people that are here, to continue talking about this, to continue talking about and working forward in extreme hazards as well as data science integrations, and exchange this information with all relevant stakeholders. Everybody is a stakeholder when it comes to these topics, as well as we need to also sort of pressure our governments to give us accurate data. Many times governments don't have the resources, right, to safeguard citizen data. So what they do is, instead of actually creating measures to safeguard data, they just put a flat no, that no, nobody gets access to anything. So it's our job as engineers to come up with methodologies and applications that keep citizen data safe, that keep citizen privacy safe, but on the same time help us create better applications for real-time response and evacuations. with that, I am so grateful for your time. Thank you so much. I know it was late, but thank you so much. Any questions? I am here to answer.
Thank you so much, ma'am, for an informative and interesting presentation. Now we can move on to the Q&A session. The participants are requested to post their questions in the chat box.
Either I was absolutely not clear or I was very clear.
Slowly they will answer. To start with the native dominant.
By the way, I hope everyone is noting down my email. If you have any questions later on, please feel free to write on that as well. There's a lot of good work happening at University at Buffalo. Nayana also worked with us.
I was
It's
just
in
about
the
to say
same
the same.
work.
It took me back years because since 2017, you kind of wrapped up all the work that we had done. And I saw a lot of Amir's work as well. So it's a kind of collaborative work. And it's got a lot of people
Exactly.
coming together to work in it.
Absolutely, exactly.
Anybody can share that feedback. Orally also can join. Maybe this new area for them. Yeah, this much of research is not going on for fire.
Mhm.
Extra crystals and all they are testing, but this is a new area, very good. They got a new idea also how to test on that, how to simulate.
Absolutely. I hope that, so for example, if students are applying for, higher education or scholarships abroad, perhaps they can use some of this discussion that we had today and write about this, because so much of this work needs to be replicated for our countries. And I mean, a lot of, and we are actually really enthusiastic about data science as well. So a lot of this perhaps can be useful.
Really thank you for sharing your time with us and experience in this developing solutions for connectivity. It's a new area and very informative. Our students will be benefited definitely. They will come back to you. And also, I want to put my thanks and appreciations to our teachers, that is, Dr. Gopalakrishna Madam and Prabha Madam, those who are organizing.
Madam, you are not audible, madam.
Yes, ma'am. Voice is very feeble.
Some net connection problem, Madam.
We are not able to hear.
Okay, okay.
Mic కొంచెం గిట్టని పోతుంది.
Mic is having the volume is
Yeah, now somewhat okay, ma'am. Speak louder, ma'am. Yeah, ma'am.
full volume only it is. So I want to appreciate our staffs, Gopalakrishna sir, Chandrakantama Madam and Prabha Madam for organizing this webinar. Thank you, Madam. Yet another webinar which is very useful for all the participants. And I am happy to understand participants from all over India have come. Apart from Haryana, they have also joined here. Thank you, participants, and this is very encouraging. And we will again come up with another technical seminar in starting of June. Madam, any feedback from the participants? We can ask.
Yeah, dear participants, some of you kindly give your feedback so that we want to really listen to your feedback and we want to improve it further. Some of you please come up and share your feedback. You can unmute your mic and speak. Some of you, please.
There is a query for you, Ramla. There is in chat box. There is
Yeah.
not.
Yeah.
So they're asking regarding do you feel it? How far can we get accurate data? I mean, some people may feel the impact usually, or some may feel like, oh my God, I've never seen such a disaster before. Very correct, Chandu. Again, so for example, for earthquakes, some people are more sensitive to earthquakes. Some people may not even feel it. Again, we don't consider it to be scientific data, which is why we don't want it to be extremely accurate. We want it to be personal, right? Because if there are, I don't know, 20 people in Buffalo that are saying that we really felt this earthquake, or well, Buffalo extreme hazards are extreme snow. Uh, but then there's a way to hang on, let me rephrase this. We don't scientifically calibrate anything based on personal data. What we do is that we say that, okay, maybe we need to put in some more sensors here. Maybe we need to get in touch with the authorities there, because more people there are saying that they had a drastic exposure or a drastic experience, right? So what it does is that it directs our data collection, scientific data collection, um, based on how the people, uh, felt it, right? So a lot of times this is to gauge what we are actually doing. Look, a lot of times, like I said, engineers work in their own silos, right? And when we're doing research, it's very easy to just get lost in the mathematics of it and never realize that, okay, real people need real solutions. That is why we as engineers and we as data scientists and we as civil engineers need to really talk to real people and get their feelings. They may or may not be engineers, so they may or may not be able to articulate what their experience was in scientific terms. So for us, it is good enough to say that, okay, how many people actually sensed this, so that we can go get access to real-time data as well. I hope I answered that question.
Sanjay Verma, now raise the hand. Sanjay Verma.
Participants, you can give the feedback.
No, I think unknowingly he pressed that. And thank you very much for giving the link for presentation by Dr. Ramla. Thank you, Naina.
Oh, definitely, ma'am. My pleasure.
Thank you so much for having me.
Thank you, Ramla. Ma'am, over to Sneha.
Yes.
I would like to take this opportunity to place on record our hearty thanks to Dr. Yes.
Yeah,
Anji.
Anju,
I want
ma'am.
to give you a feedback.
Yeah.
Yes, ma'am. Yes, ma'am. I want to give you a feedback about this international webinar, ma'am.
Please, ma'am.
Thank you. Thank you. Thank you, ma'am. It was pleasure to giving me this opportunity. I'm Dr. Anjishwari, working as a guest lecturer in Anna University, Madurai Regional Campus. I'm pleasure to be part of this international webinar on innovative technology and civil engineering. And first, I congratulate the EASWARI Engineering College Management and HOD ma'am and the coordinator Chandrakanta ma'am and the staff members who are working hard for past 7 days. Some of the topic which I had known in detail, like high performance concrete by Somnath Ghosh, artificial intelligence and immersive technology in civil engineering by Janathanan sir, Dr. Janathanan sir, and he played a special game with us, and it was very interesting to spending time joy with effective and And then special topic is India's first geopolymer building by Mohammad Zabur, etc., etc. All the speakers are given their wonderful knowledge with effective, wonderful knowledge. And with wonderful slides and videos, it was easy to understandable, which is related to advance in civil engineering. Once again, I congratulate Dr. Gopalakrishnan sir and fantastic teamwork. I thank HOD ma'am once again for giving me this opportunity. Thank you so much, ma'am.
Thank you, madam.
Thank you, ma'am.
I'd like to
Thank
say,
you so much.
yes. I'd
Wait,
like
wait, Sneha. Sneha,
Yes, ma'am.
1 minute.
Yes. Yes.
Any more participants to come up with feedback, please?
Yes, madam. This is Brahmachari from KL University.
Thank you. Please. Go ahead.
I thank you for being such an amazing speaker and for your great session, madam. I feel so fortunate to have been placed to your international webinar series and thankful because of you are truly a wonderful speaker. And I enjoyed your sessions like these intersections of structural resilience and data science and the AI and VR in construction industry and sewage sludge as a sustainable resource and lightweight aggregate. Those sections are enlightened me. Knowledge was great ahead, madam. Thank you for giving this opportunity. Thank you a lot, madam. And
Thank you, Brahmachari
thank
garu.
you, organizing team.
Thank you, Brahmachari garu. Thank you for coming from KL University. Thank you.
Thank you very much, madam.
Koner Lakshmaya University from Vijayawada, ma'am.
Yes, madam.
Okay.
Any other participants? Any other participants? You can give the feedback, please.
Hello.
Hello.
Yes, sir.
Ma'am,
Yes, sir.
myself.
Yes, sir.
Yeah. Carry on, sir.
You organized a very good informative session, ma'am, and
Thank you, Brahmachari garu.
very good informative session. Thank you, Ramla madam, and organizers. Thank you.
Koner Lakshmaya
Okay.
University from Vijayawada.
Thank you.
Good evening, ma'am.
Thank you, sir.
Hello, ma'am.
Yes, sir.
Yeah,
Sir, carry on, sir. Thank you, sir.
I'm
Carry on.
Harunal Rashid from Guwahati, Assam. So, first of all, I want to thank this Shri College of Engineering. It is very nice. All the sessions are very nice. And I find myself in the primary school of civil engineering only. You are giving the topics are so high level topic. Whatever we have studied earlier and now what is happening. So I find myself very much enjoying in all the sessions, and especially thanks to Ramala Qureshi ma'am. So very nice lecture, and I'm very happy to find all the lecturers, all the experts in this all the sessions. And thank you, ma'am, very much. And I want to have more similar webinars ahead. And also, I want to send students from my state to your college also in future. Thank you, madam.
Thank you. Thank you, sir. Thank you so much, sir. Anyone else? Ma'am, shall we go ahead, ma'am? Okay, ma'am. Over to Sneha.
Yes, I'd like to take this opportunity to place on record our hearty thanks to Dr. Ramla K. Qureshi for the elaborative lecture and guidance she has extended to all of us. And I'd like to thank Naina, who is a proud alumni. I also extend my gratitude to the management, principal, vice principals, deans for giving us this opportunity to conduct the international webinar series. I also thank HOD ma'am for the continuous support. I thank coordinators and faculty members for the successful completion of the international webinar series. Finally, the participants for the fullest cooperation. Thank you so much. Now, the participants are requested to fill and complete the feedback link, which is available in the chat box. Thank you.
Thank you. Thank you.
Thank you, Ramla. I think
so much for
today is a
having
working
me.
day for you. You are spending the very precious morning time with us. Thank you for coming.
Yeah.
Thank
Thank you.
Absolute pleasure. if anyone has any questions, please feel free to write to me.
Yes, madam. We will share your links in the chat box so that
Yes, please.
they will be calling you.
Awesome. Thank you. Thank you so much.
They will contact you. There are 10% they will react and they will be working on these lines. This is a very unique topic for us. Not much work is going on in this area. Thank you.
Thank you so much for having me. Have a great day, everyone.
Yeah, thank you, Ramla Qureshi, Dr. Ramla Qureshi. Thank you, Nayana. It's
you,
our
ma'am.
pleasure to have you with us.
Thank you
very
so much, Ramla, for coming in.
Yeah, thank you very much for accepting our invitation.
Absolutely.
Yeah, thank you. Thank
Please
you
take care.
all. Thank you all.
Nainashi, thank you, ma'am. Thank you.
Definitely, ma'am. It's such a nice collaborative work of all calling in international speakers and all. It's really great, ma'am. Good conduct. Congratulations on the good conduct of the 2-week program.
Thank you. Thank you. Thank you. Thank you. I'll catch you up through mail, Ramla, Dr. Ramla, and Dr. And my going to be Dr. Nayana.
Hopefully soon.
Yeah. Thank you. Thank you.
Next year season, we can call Naina to share
Yes,
her.
ma'am. I told her, ma'am, already. I told her already, ma'am. Next time going to call you, Naina.
Chandrakanta ma'am has pre-booked me 1 year ahead. She's like, don't give your slot to anybody. I'm the first in line.